Hi, good morning, Professor. This is Vinay from IIT.
Good morning, Sanjay. Good morning, Vinay.
Good morning, sir.
Good morning,
Good morning.
everybody.
Good morning.
Very good morning, everybody. So we are almost set for this week now. Second week, Sanjay. Thank you very much.
Yes, I'm happy to present here.
Oh, this course is really going very well. The kind of responses we are getting from the participants are very positive. We have received a large number of responses from participants. Good to have you, Vinay, for the session this morning. Thank you.
It's nice to know.
Today, Arijit supposed to announce something. You told that.
Yeah, he probably will make that announcement either today or maybe tomorrow or day after, but sometime this week, certainly.
Oh, okay.
Yeah. Maybe tomorrow or day after. I think Sunil is traveling today, if I'm right. I'm not too sure.
Mhm.
So we are just finalizing the poster for the
Okay.
anniversary colloquium. And as soon as it is finalized, I think it will be announced. But it's, you know, it's almost ready. I think they were only inserting the final titles of the talks and that kind of thing. It is 10 o'clock and should we start, Sanjay and
I think
Vinay?
we should start because let people join.
Yeah, so good morning to everybody and very hearty welcome to the second week of this course. And I would like to first thank a good number of participants who have sent their feedback. And we have received feedback from very many of you, and it is very positive. It's very encouraging, very gratifying. And somebody who has known Sanjay for a long time, I feel very proud that his course is so well received by everybody. So Sanjay, congratulations for an excellent course. And I'm really so happy and proud that a large number of students and some postdocs also amongst the participants, some faculty members as well. And all of us have learned many things. You're covering it brilliantly, which is, and your the files that you're sharing, the tutorials you have organized, I think it's an excellent program. We are also receiving a large number of requests to organize similar courses in the future. And I would like to assure all the participants that CAMOST will make every effort to do that. So let me not come in your way. And I am very happy to invite Sanjay to please continue the course. Sanjay.
So good morning. Let me share my screen first.
Sanjay, we are very fortunate to have Vinay with us this morning. He will be assisting the session. And
Yes,
yes,
thank you, sir. I'll take care of the question and answers.
yes, thanks, Vinay.
Let me see that. Are you able to see my screen?
Yes, we can.
Yes, it is good. You need to go full screen.
All right. Right. have to do certain things. Okay, it is here. So first of all, okay, just okay, now it has come here. Mm, Fine. So let me start. Good morning, everyone.
I think your screen can become slightly larger, I think. Are you? Yeah, this is good. This
Is it
is
right?
good.
Oh,
Yeah,
I think I did it wrong.
yeah,
Or ulta actually, opposite.
yeah. This
Okay.
is fine.
Okay. So good morning, everyone. So hearty welcome for this sixth lecture or sixth class, what I should say. So here I would like to say that today we'll be circulating the third assignment, okay, which will be discussed in Wednesday. Based on this, whatever we will be discussing today and tomorrow, it will be problems will be given. Okay, so please work out them. Okay, at least by before coming to the tutorial, it will be helpful for you to understand thoroughly. Okay, also I'll give subsequent material from the different books. So those actually are interested, please go through them. Okay, so nothing can substitute like reading books. So I think that is a good habit, and you can get it from there. If you have any questions and doubts, please raise your questions either in a tutorial or in the next classes. So today, what we'll discuss today, we'll discuss something which is really quantum. Okay, so there is no classical analog for this. Okay, in optics. So what is that? In one of the last week's classes, what we discussed that that the two quadrature, right? One is position quadrature and momentum quadrature for the ground state, or which you also say that zero photon state, they are same. That standard deviation or dispersion are same, and which is actually satisfying the minimum condition of the Eisenberg answer relations. And these values, dispersion values for the canonical conjugate operators Q and P are square root of h cross by 2. Also, we saw that if you consider coherent state, which we are denoting by alpha here, okay, and also we discussed in the class as alpha, which alpha is any complex values, okay. Then also we see that these dispersions of position and momentum also same for the coherent quantum coherent state, and that is also square root of h cross by 2. Then we ask the question that is it possible to beat this limit either of the coordinate, because we can't beat the both of the coordinates, like both of the quadratures, what I say, that either position quadrature or momentum quadrature, okay. So either of them can we beat it. So then we had shown the example. This is only possible in the quantum mechanics by superposition theorems. As an example, what we showed that if you just superpose the zero number state and one number state, that means there is zero photon and one photon state with proper superposition coefficient, this what square root of 3 by 2 and half. Then we showed that position quadrature, okay, dispersion values coming out 3 by 8, which is less than half in the unit of h cross. So that means whatever we have got it, that position quadrature dispersion, that square of this variance, okay, is h cross by 2, okay, and if you take the standard deviation, which will be square root of h cross by 2, so that actually you can squeeze it, you can make it smaller if you have the superposition of the two number state, and that is specifically this kind of things. But as you understood that this can't be automatically happen. It actually takes you that some of the extra things which is in the momentum quadrature. Okay, that means at the expense of the momentum quadrature, where actually the dispersion is more than half in the unit of h cross, that means that your momentum uncertainty becomes larger compared to the either zero photon state or quantum quantum state. But with the expense, you could squeeze the position quadrature. So that's a big achievement and which can be demonstrated also. Okay, so that's actually good observation. Okay, from the quantum phenomena of the optics. Okay, what you see that if you just change this 0 and 1, okay, that 0 state and 1 state, okay, and you will see that you are getting this one. What I'll say is that you work it out and you will see that this combination will give neither position quadrature nor momentum quadrature squeezing. So that's an interesting point that you need to have proper superposition, okay, to get the squeezing. Okay. And also you can try with some factor. So you can put alpha 1 here, alpha 2 there. So not alpha, so A and B's, let's say. And put that superposition of the vacuum or zero photon state with the any coherent state alpha cell and check what coefficient will get the squeezing in either of the quadrature, and that will give you nice feedback in the in future. Okay, that like if you consider alpha to be one laser light, a classical laser light, okay, and if you are impinging this to a beam splitter and there is nothing in the orthogonal port, that means that there is a vacuum is there. So with the proper superposition, you may get the squeeze state. Okay, that's a one hint. Let us give it now itself. Okay, so we'll see in the later. In 1985, this famous paper by Schlosser and group, okay, has changed the total understanding of quantum mechanics in the or optics sciences, total understanding of the optics in the domain of the quantum phenomena. Okay. They are the first to actually show that it is possible to generate this quantum squeeze state using four-wave mixing inside the optical cavity. So they can be called as a further of this new generation of the squeeze light. Okay. Now let us discuss that. Okay, we have understood that with the 0 and 1 photon. Okay, can we just realize this for the any number of photon? Okay, so if we just say that, just say consider any number state. So n is the number state which is the eigenstate of the Hamiltonian. Okay, so what we know that we will get the eigenvalue n plus half in terms of the h cross omega, okay, times n. So h cross omega should be there here. Now, if we just try to find out that the dispersion in the coordinate quadrature, then you just calculate. So what you will see that since the mean value of the number state at the coordinate quadrature will be 0, as you understood that you can replace q by square root of h square by 2a plus a dagger. And if you don't have a square here, what would happen that a and a dagger either create or excite the system, or it will be excite the system. Okay, that means you either create extra photon or it will annihilate one photon. So that means that this quantity, mean value of the coordinate quadrature with respect to number state will be 0. So that shows that this deviation, this variance, okay, should be equal to the q square value. And if we just calculate this, okay, what you'll see that you will see nothing but that h cross by 2 in 2 a dagger a plus 1 in. So a dagger a is nothing but number operator which will give the eigenvalue in corresponding to the number state in. Okay. Similarly, if you work out for the momentum quadrature, you will get same value. So both in both cases, what you will get h cross in plus half. Okay. So what you see that for number state, okay, you will get the uncertainty in the both momentum and quadrature, momentum and position quadratures. Okay, they are same, and they you will be square root of n plus half. So what for n equal to 0, you saw that you will get h half h plus omega was the minimum energy, and square root of h cross by 2 is the uncertainty which you got it. Now that for that will increase, this uncertainty will increase as you go for higher and higher number states or energy number state. Okay. So here what you see that if you just talk about the amplitude fluctuation, okay, which you can write of the electromagnetic field, okay, light, okay. So what you see that you will be able to write in terms of a square plus k square. So that means that ultimately that will go by n plus half square root, okay. The fluctuation, so this is variance, so fluctuation is the standard deviation, okay. And in the as I said that for mean value of the position coordinate and momentum coordinate will be 0 with respect to the number state. That means if you want to plot them in the phases space, okay, of momentum and position and momentum quadrature, what you will get? You will get a circle, okay, with a fixed radius in plus half square root of that. And what happened to the phase? Okay, phase of this the field, electromagnetic field corresponding to the number state, that can be anywhere in this. So theta can or phi can be anything anywhere here. So the amplitude, okay, what you will see that amplitude is perfectly defined for the number state, but phase is completely uncertain. Okay, so this is the phasor map what we will get in terms of the the number state, okay, where you will get a circle with the radius n plus half square. Okay. So what we can say that for number state, okay, that your amplitude variation are fixed. You can't go beyond that. And if you increase n, your radius of uncertainty will increase and increase like that. So if I compare now this number state with the coherent state, this has some differences there. As you have seen that if you consider a single mode coherent state, which is nothing but the eigenstate of the annihilation operator A, okay, and you will get that A alpha equal to alpha alpha. Alpha is any complex quantity, and the number state you can write in terms of the coherent state you can write in terms of the number state. And if you want to plot this number state, okay, what you'll see that you'll be having some kind of a Lorentz profile, and as you increase the number of increase the value of the alpha, it will turn out to be Gaussian profile. Now, in terms of phase space, as you have seen that if I want to plot the Q versus P or P versus Q, okay, what we will see that the amplitude, which is nothing but square root of P square plus Q square, okay, so that will be in the radial directions, and phase will be around the phi direction, azimuthal directions. So if I want to make this uncertainty of the quantum coherent states, and what you will see that for different values of alpha, what we will be able to get, the position of this alpha anywhere around this, okay, around this rings, okay. So that means what you will see that you will be having different phases, but amplitude of uncertainty will be fixed. However, as we have seen that if you want to calculate the momentum and position uncertainty, okay, those will be fixed by the value square root of h cross by 2, as we have seen. But amplitude will be fixed here, okay, in this range, okay, and the phase uncertainty so will be there around this ring, okay. So if I want to see if you want to see that the propagation of the quantum state, which we can write is alpha e by I omega t. So once omega t is varying or t is varying, this total value will be modifying. So what will you get? The different values of alpha will get different points inside the ring. Okay. So around this different position values. Okay. So ultimately, what would happen that what we'll see that this quantum state, okay, if you talk about electric field, okay, so it's actually the amplitude variations, okay, what you'll see that is fixed over the evolution of the quantum state over time. Okay, this is the time axis. Okay, but that since there is a sinusoidal part is there, okay, it will oscillate. Phase will be oscillating. Okay, with the sinusoidal part. So that's the actual picture which will see that for quantum state. So as you see that in terms of, I'll just again repeat, in terms of the position and momentum quadrature, those values are fixed. Now what we are plotting here in terms of the amplitude and the phase. Okay, when you are talking about amplitude, which is square root of e square plus q square, and phase will be tan inverse q by p by q. Okay, that will actually, if you just work it out, you will be finding that amplitude, okay, will be same over the time, but phase which will give the oscillation which is changing. Okay, so that's actually, if you see this amplitude is fixed, we will be able to say that, or if you see that this dispersion of the electric field, okay, or light is same over the evolution of the state, okay, then you will say that this is quantum state. But what you see that in the case of the squeeze state, it will be different. Okay, so that will come. So as you understood that squeezing down means physically we are squeezing the state. Actually, we are squeezing in the momentum or position quadrature. Okay. Ultimately, what you can say that as I showed in the last slide, you can write in terms of the amplitude or phase. Okay. So either of them. So here you see that once you squeeze on one of the quadrature, either momentum or position, you will get that this kind of feature. Now, let's say that what happens to the squeeze state? What are the properties? Okay. Once you understood that squeezing means either amplitude squeezing means that you are actually somehow trying to conserve the energy, trying to put all the photon in a small space. Okay, so you are actually the number of photon you are increasing in the state. Okay, so that if you want to increase the number of photon, what would happen that keeping that idea that your energy is conserved, okay, then what would happen that you have to start with the gas energy of the photon is goes by h cross omega. So somehow you have to make from 1 photon to 2 photon or 1 photon to 3 photon like that, because you have to conserve the energy. So if you want to increase the number of photon, so you would look for the nonlinear process. Nonlinear process means from 1 photon you are going to 2 photon or more. Okay, so there is fortunately there is a scheme available for this kind of nonlinear process, which is known as parametric oscillation. What it can does, suppose you have a crystal which has the non-zero chi2 value, okay, in terms of the polarization, okay. So what would happen that if you shine one pump laser light like this, okay, what you will get, actually you will get two photons or two lights, okay, one will be signal, one will be idler kind of things. And that is well known in the parametric oscillation. Okay. So that is the availability that using one single photon, if you want to pass it through the nonlinear crystal, okay, the nonlinear crystal available whose actually chi2 is non-zero, and then it is possible that you can get a two photon having the same frequency also, depending upon the crystal. And we will see that how it is possible, okay, in terms of atomic structure, okay. So in terms of, let's say that in nonlinear crystal, what you can show that if you shine that one laser light from here and another laser light from here, okay, once it goes to the nonlinear crystal, okay, you could gain, okay, either another laser light here, which is having the addition of these two laser light frequency. So, and unfortunately here both the laser lights are omega 1. So we will have that total light which is coming out as a 2 omega 1. You could make that a different combination also. You could have that one light coming from here, another light coming from here with a 2 omega 1, and you will be able to get another omega 1 emitted from this. So different combinations are allowed. Okay. And how do you understand this different combination? In terms of the atomic structure. Atomic structure, if you remember that we can have that absorption of the photon, okay, as we have seen in the last slide, that photon is coming to the crystal and it will excite the system by allowing the electron going from the ground state to the excited state. And subsequently, what would happen that depending upon atmosphere and depending upon the system, okay, you can have the spontaneous emission or stimulated emissions. So let's say that you are having emission. So emission can be coming down to the, bringing down the electron to the ground state and emit one photon. Okay. So here is a single photon excitation process. Similarly, if you can have that, you can allow like a Rydberg state. Okay. Earlier, because of the non-availability of the some particular kind of a laser light which can excite from down state to the excited state of a Rydberg atom. Okay, so used to use that two photon cases. And what would happen that using the two photon, it can go to the higher excited state, and from there you can get the emission. Okay. Similarly, you can have that here two similar omega. You can have different. You can have different omegas. You can have similar omegas and get the conservation of the energies. Okay, which actually tell you that emitted photon will have the frequency which will be adding of the incoming photons frequency. Okay, so that is the scenario here. So similarly, what you can have in a reverse process also possible. You can have the 2 omega coming and 2 omega 1 photon is coming with a frequency 2 omega, and you will get a 2 photon having each one having omega. So both the process is possible in the atomic cases, and that actually lead to the nonlinear process. Okay, in crystal. Okay, let's look at it in the second quantized formula. So I hope that is understood how one can have nonlinear process and generate 2 photons from 1 photon or 1 photon from the 2 photons. Okay, so that's understood. Now what we can have, can we just write this process in terms of the second quantized form? So consider the pump is coming, and there is a quantum operator, okay, in terms of the creation and annihilation operator. Let's associate B operator with the pump. Okay, so that means that your light is coming this way and annihilating into the crystal. So B, that annihilation operator, is associated with that. Now, if I have that 2 photons which are coming out having each having same kind of photon, like each of them having frequency omega, what we can have that we can associate it the operator, the creation operator, annihilation operator A, the annihilation operator A with that. So if I just write it down, what would happen that in terms of interaction Hamiltonian, okay, we can write that B is annihilated, okay, and 2A is created. So that you can write that B annihilations along with the creation of that 2A one after another, or we can have a reverse process that 2A is annihilated and 1B created. So interaction Hamiltonian can be written B A dagger A plus harmonic conjugate of that. Okay, harmonic conjugate are nothing but the opposite reverse process. Okay. Now, using this kind of process, as you see that inside that crystal, you have a many atoms are there, and many atoms are going through this kind of process. So what we can have, anyhow, this there is a things which we can do it. That some simplification for here. If we consider that your the palm laser is very strong, okay, and this is the point laser light, okay. So then what you can show that, as we had shown earlier, that you can write this in terms of the so if you can write the strong laser is beta, okay, and beta is nothing but the eigenstate of the B, okay, with the coefficient with the eigenvalue beta, okay. Then what we can show that, as we have shown earlier, that because it is actually dominated by the large number of photon, so this number state, okay, beta can be also thought about the eigenstate of the B dagger. Okay, so with the eigenvalue beta star, the complex conjugate of the beta. So what we saw it here, that here for a strong laser light, beta, okay, which is actually representing the coherent light which is impinging on the crystal, okay, can be understood as a eigenstate of the B operator or B dagger operator, depending upon on that we will have the eigenvalue beta or beta star. Okay. So what we can have that for these cases, okay, for a strong laser light, we can substitute that, okay, in the operator, and if you substitute, what would happen in general form? What you can write? Let's say that we are writing in terms of beta equal to R by 2 e to the I phi. So what would happen that you will write that, sorry, your A dagger square, A dagger is square e to the I phi is coming from this beta star, okay. So, and you will get the amplitude R by 2. Similarly, for the first term will be A dagger square e to the minus I phi and with the amplitude R by 2. So this interaction Hamilton, which you saw that, which you understood from the this kind of a cartoon, okay. So we will be able to write them in terms of the creation and addition operator of the outcoming of the two photons having similar properties, okay. And in these cases, as you remember, you have to consider that your in the incoming pump laser will be very strong. Okay. So if you have, so ultimately what you will have, that you will have this kind of process going on infinite number of times, so that this one, okay, you will be able to write, okay, you will be able to write in the form of exponential, where this process is going in the number of times, okay. So it can have a possibility that one, there's no process like that. You can have that single this process going on. You can have this process going on 2 times. So all the possibilities, if you add, it will come in the exponential form. And these, so this one, okay, what we are saying that, because we understood that squeezing of the light means that you are creating more number of photons from a few number of photons. So this is the way one can create the squeezing, and we want to write this operation, okay, using the A and A dagger, okay, is as a squeezing operator, and we'll see whether really it is squeezed in terms of that, whether it is increasing the number of photons or not.
Excuse
So,
me.
yeah, you have any
Uh,
questions?
yeah, I think there's a question in the chat box. So the question reads, Sir, what is the importance of virtual state in SHG and SFG? Also, how does it differ from two-photon process?
Sorry, what is the importance of virtual state?
Yeah, virtual state in SHG and SFG, and how does it differ from two-photon process?
SHG means
I
the
think the second harmonic generation and some frequency generation.
harmonic generation. Oh, okay. Second order harmonic generation. You're saying. Okay. So this is what you see that is second order harmonic generation is going on. Okay. So that here you can have that you can have the two photons coming out from the single photons, as you saw in that case of the also in the atomic cases. And another one is frequency generator, isn't it? What do you say?
Yeah, some frequency generation.
Frequency generator, and what is the difference he asking?
He's asking what is the importance of virtual state in these two cases.
Oh, virtual state, right? Okay. So that actually, okay. I didn't go through that. The virtual states actually, what would happen? See, all the two photon kind of interactions. Okay, virtual state is important. Here, what would happen? You can have this, as I was explaining that you can have this process infinite number of times. As you see that from one photon, it has gone two photon, and these two photon can actually combine and giving you one photon back in the same crystal. Okay, so you can think about these photons, okay, are as a virtual state. I don't understand that are you referring to that virtual state or some atomic state as a virtual state. If you understand, telling that these photons which are generated intermediate level are the virtual state, I think that is that these two photons which have been generated can combine again, okay, and give you the single photon. And again, then so they are like a pair creation and pair annihilation. Those processes are going on infinite number of times, and that's why you are getting that total operator is in the formula exponential. Okay, so I believe that was the answer, but I am not sure whether the question is referring to that, because what virtual state he is referring, that is not clear to me. Okay.
So
Maybe at the end we can discuss.
yeah, if the student wants
Okay.
to, then check.
So any other questions?
No other questions so far.
Oh, thank you. So if you see that that the operator, okay, having this exponent as operator, okay, and this is if you write a e to the power a, and a is a Hermitian, so making that this is an operator which referring to the I'm just referring to now, just defining, but I didn't prove it. Okay, it is a unitary operator. Okay, so that means what you can check that is that R is nothing but S inverse R. Okay, and is also can be obtained by replace R by minus R. So here R is nothing but, okay, that one parameter which actually tells about, okay, as you see that how much squeezeness is there. Okay, so we are yet to see that. Okay, so what you see that up to now you saw that intuitively how this operator has been constructed from the idea of the second harmonic generations. Okay. Now, if I just operate this SR operator, which is I'm telling that is a squeezing operator on vacuum state, and then you just operate, as you see that this contains infinite number of creation and annihilation operator, and all of them, as you see that square, means that either it will create two photon or it will destroy two photon. There is no chance that it will annihilate a single photon or create single photon. So these creation and annihilation is come with a pair. Okay. So ultimately what you expect that when you sum it up, you will have that number of states, okay, will be in the even number of states. Okay. So since they are actually in the pair, they are creating annihilating. Okay. And there is a factor coming in front of that, that goes by tan hyperbolic r to the power n. So what you see that summation over n is there, not only that, and tan hyperbolic function is actually tangential. So it goes shoots up. Okay. So that means that if you have a vacuum state, if you operate squeezing operator, you will create infinite. There is a possibility that you will create infinite number of photons. Okay. So that is a possibility that you can create and destroy, create, destroy. Okay. So that's actually the understanding that this can be used as an squeezing operator, and it shows that actually squeezing means that you have to create number of states, extra number of particle. Okay. So this if you increase the R value, what you see that the coefficient of the coefficient increases, okay, shoots up, and that means that if you operate the squeezing operator on the vacuum state, okay, so what you will get, that is the possibility that you will get infinite number of photons, okay, and that is called as squeezed vacuum. So if you operate on the vacuum, okay, you will get squeezed vacuum. So maybe you can look at the Professor Catalyst lecture, non-classical light in the YouTube, which actually explains these ideas. Okay. Now, once you understood, I believe that you can go to the how the transformation is happening in the different position and momentum quadrature. So if you look at this operator and operate in the position quadrature, using the Baker's house of expressions, what you see that, and you can just apply it here, and I will ask you to work it out. Ultimately, what you see that nothing but Q e to the minus R. Whereas in a momentum quadrature, what you see that P e to the plus R. That means if R is greater than 0, R can be any values. It can be positive or it is real value. Certainly, it can be positive or negative. So depending upon the R positive, what would happen that this operator is on the position quadrature squeezes the position quadrature. So it is actually position squeezing. Okay, you can say that it is squeezing the in the surface or in the space. Okay, whereas at the expense, certainly it has to be relaxed in the momentum. Okay, so what you see that certainly that momentum quadrature, okay, for R greater than 0, okay, this is relaxed or amplified. Okay, and if you see that in terms of the uncertainties, okay, what you will see that if you operate in the position quadrature, okay, the dispersion will make that this kind of R greater than 0. Okay, so what will happen? I think this wrong picture is coming. Okay, this will be opposite directions. So you will have the momentum relaxations, and ultimately, so this will be of the quadrature, the position quadrature. So this will be vertical. This green shadow line is vertical. Okay, so that you will have the this is actually for the momentum squeezing. Actually, we are showing. So this is for the R less than 0. R less than 0, what would happen? That you will have the momentum squeezing, and what would happen that your, as you see that your spread in the momentum axis, okay, is squeezing at the expense of the amplification in the position quadrature or position axis. Okay, so that is actually the uncertainty or the dispersion, okay, in terms of the position and momentum, if depending upon whether R is greater than 0 or less than 0. So this picture is for the R less than 0, and this picture is for the R greater than 0. Sorry, I think this is actually, this will be plus and this will be minus. Okay, so that's a confusion I made. Okay. So, so this is for the plus and this is for minus. Okay. So what you see that you can make, okay, squeezing of the particular quadrature of the vacuum state, okay, that by changing the value of the R from positive to negative. So, so what you understood that operator, okay, now SR can be called as a squeezing operator because it squeeze the dispersion of different quadrature, either momentum or position quadrature. Now let's see that. So what we saw that this is the expression for the momentum and position quadrature after the operation of the squeezing operator SR. Okay, and as you see that it's the squeeziness depends upon the how the value of R changes. Okay, or negative, positive. Okay, or if you increase the value of R, it squeezes further. As you saw in the last, it will be a minus R. If you increase the value of R, okay, it is squeeze this quadrature. Okay, the R increasing value is be squeezing quadrature, and at the same time it will be amplifying this one. Now we can also write the position and momentum quadrature in terms of creation and annihilation operator. So if we write, what we will see that as we are seeing that saying earlier in the when you are operating the ASR on the vacuum state, the vacuum state, number of photon increases. We realize this here also. Okay, we see that creation is multiplied with the cos hyperbolic R. Okay, it's increasing. Okay, with the number of with the value of the R. Okay, so similarly that it will be for the annihilation operator also increase. Okay, so if we want to see in terms of electromagnetic field, okay, what would happen? So if you remember that in the electromagnetic field case, okay, we could write that the field operator, okay, or radiation operator in terms of polarization, then amplitude, complex amplitude, okay, which we are saying that operator form, okay, and there is a propagation terms, okay, and that complex conjugate. Now, what would happen? Also, I just explained to you. You could write that the amplitude term, which is a complex quantity, in terms of the dimensionless operator alpha, with the prefactor which takes care of the amplitude of the electric field by n. Okay. So if you would write it that way, okay, then what you will see that you can write this dimensional operator of the field alpha in terms of the Q and P. Okay, just it will be QL plus IPL by square root of 2H cross. Okay, and what we know that from the operation of the squeeze operator on the position and momentum quadrature, either you can operate directly there or you can write this position and momentum quadrature in terms of any creation annihilation operator like and then operate it like this way. Either of the way, okay, we can do that. The how much will be the effect of the squeezing in the dispersion of the electric field? Okay, so what we will see that that we can write to calculate that we can write that electric field has the two component. One is the position component, one another is the momentum component. Where position component quadrature we can write from here, as you see that it will be q times e to the power I k r, okay, minus I omega t, and there is complex conjugate which will be having the q dagger, okay, with the minus sign of this one. So if you combine that, what will you get? You will get expression, okay, where EQ is nothing but you will have a e to the I omega t and a dagger, okay, e to the minus I omega t. That is in a position quadrature. Similarly, you will have the momentum quadrature. You can write it, okay, e to the I omega t plus a dagger e to the minus I omega t. So you can write that the component of the electric operator, electric field or electromagnetic field operator, okay, in terms of the position and momentum quadrature, okay, by this fashion. So once you just separate them out, okay, we want to see that how these two quadrature, okay, which you will be canonically conjugate to that, okay, can be transformed under this squeeze operator. So we have got this EP and EQ. Now, if we just see this operation, okay, in terms of the um, uh, uh, in terms of the your vacuum state, okay. So what you can show that if you see that in terms of vacuum state, it will be nothing but n square. This you have seen. And similarly, in terms of the coherent state, is also n square. Okay, but you can check that this one. Okay, now you want to work. Okay, in terms of the vacuum and coherent state. Okay, both of these quantities will be greater than n square. Okay, so these two quantities are not actually now okay the minimum uncertain state, but okay, what would happen if you add them up? Okay, then we'll see that this is coming to the n square. Okay, and in terms of the squeeze operator, okay, or if you write that the squeeze operator on vacuum state is giving you the R state, okay, what you'll see that you will get that nothing but extra quantities which you actually can understand or derive, okay, from the last expression where you just express that E in terms of Q and P. Okay, if you just look at, sorry, I'll go back. So if you see that this, if you just write this in terms of Q and P, you will get cos term and sine term. Okay, so that actually you can get it here. Okay, when you write this one, okay, you will get cos square minus I omega t in the P sector or Q sector, whatever. You just check it, and another term will be that the sine square I omega t in the conjugate canonical conjugate sector or conjugate quadrature. And one of the quadrature, as you understood, okay, will be amplified, another will be squeezed depending upon value of the R, whether is a positive or negative. Okay, so then what would happen that you see that operating the squeezed operator on the electric field variation operator or fluctuation operator. Okay, what you will get, that you will get term like extra terms compared to when you take the expectation value with respect to vacuum or the coherent state, the extra factor is coming. Okay. So now what you got, this extra factor is nothing but coming from the two different quadrature sectors. Sorry, I think that this is with P. Okay, one is Q and another is P. Okay. So you will get a different quadrature. So what you will see that if we just calculate for the momentum quadrature, okay, this is the first term which is coming. And position quadrature, it will be second terms. Okay. Now, if I want to plot them, okay, this position and momentum quadrature of the electric field operator dispersion, okay, what I'll see that, let me write it once again and see the graph. Okay. Let's say that consider R is 1/8. Okay. And what would happen that you'll see that blue line is the momentum one and red line is the position one. And what you'll see that wherever the blue line is picking up, red line is going down. Okay, that means that this one, okay, the wherever momentum quadrature is amplified, you will get the squeezeness in the position quadrature, or wherever that you will get position quadrature amplified, momentum quadrature will be reduced. Okay, so what does it mean? As you see that this variation of position and momentum quadrature at different time, you see that here it is x-axis is with time. Okay, so if you see that the position and momentum quadrature of the electromagnetic field variation or fluctuations, okay, that varies with respect times. So if you can make the system, if you can make your light such that it is squeezed in the position quadrature at particular time t equal to 0, you will see that after certain time, actually it is gone opposite, that your momentum is actually got squeezed and that position is amplified. Again, what happens if you have to wait for some more time to get that squeezeness of the position. So it is not that once you prepare the system, okay, in the position quadrature, it will be there for a long time. So you will get actually the oscillation between the squeezeness between position and momentum over time. So that is the one of the important feature of the squeezing operator operating on the electromagnetic field or light, and that has to be understood very clearly for different experiment of like gravitational wave experiment. So what would happen? So in that cases, when they actually do the Michelson kind of interferometer, okay, they have to look for the where and when, not only where, when actually the squeeziness is coming in the position quadrature. Okay, so they have to wait and see the observation of the position of the displacement of the atom. Okay, when actually you will get a squeeziness in the light. Okay, in the position quadrature. So, and they have to wait till the like omega t becomes pi to get it again. Okay. So it is not the continuous observation. Okay, they will have a periodic observation to see this light. Okay, squeeze light in the position cases. Okay. I believe you have understood this feature. If you have not understood, please raise it again in the tutorial. We'll try to explain again. Okay. So this is the feature actually which we have to understand very clearly, that squeezing the particular quadrature is not a permanent. Okay, it actually oscillates between sorry position and the momentum. So if you see in terms of picture, what you will see that position and momentum, okay, quadrature oscillates over time. So I believe you have seen this picture. Now let's see that some of the properties of the squeeze light. And let's concentrate for the first one is the vacuum squeezed. So if you just if you have understood that how this squeezing operator act, okay, SR acts on the momentum and position operator, which you can convert in terms of the creation and annihilation operator. So you can easily calculate that what will be the population or intensity of the squeeze light. Okay. So that means that we have to take the expectation value of the number operator with respect to R, which is nothing but squeezing operator on the vacuum. So R is nothing but squeezing operator on the vacuum. So what will happen that if you squeeze the vacuum, what will get? You'll get sine hyperbolic R square. So this profile is looks like this one with respect to R. So as R increases, okay, it will increase like parabolically going on. So it's shooting up. Okay. So that means the population, okay, depending upon the squeezing of the value of R, okay, increasing exponentially. Okay. Similarly, if you want to see that, if you want to see that if you squeeze sufficiently, that means if you are squeezing to the infinity, R goes to infinity, what would happen that, okay, your position quadrature, okay, will be becoming Q only, Q operator only, okay, because R goes to infinity, okay, and um, which sorry, I think R goes to infinity. It is one of it. It is coming out to be this will be zero kind of things. Okay, so Q times zero, it is zero. Okay, so what would happen that this is so Q equal, that means you will get Q equal to zero. Sorry. So ultimately this will be Q. So this will be you will get this position quadrature will be zero. Sorry, there is misunderstanding here. Here what happened that you make this position quadrature, okay, squeezing, okay, by putting R equal to infinity. That means that your spread or dispersion in the position will be very zero. And what does it mean? That your spread in the Q sector will be zero, and that means that you are getting P equal to zero straight line. Okay, that Q equal to zero. So there's a mistake here. Q equal to zero straight line. Okay, so that is actually the Q equal to zero straight line. Okay, so that's actually squeezing. Okay, so you are spreading that. Okay, spreading the uncertainty in the momentum sector and squeezing in the coordinate sector. So that's so that is spreading. What you see that there's a mistake here. Okay, So it will be Q equal to 0. So you are spreading in the momentum sector, and if you are spreading in the momentum sector, means the kinetic energy of the particle shoots off. Okay, and what we will see that in terms of the energy with respect to R, okay, you will see that there are a lot of the kinetic energy shooting off. Okay, uncertainty in the kinetic energy shoots off in the system. So this was one. If you want to do, suppose trying to see the position of the atom inside the crystal using electron microscope, where actually you are trying to observe the locate the position of the atom inside the crystal. Okay, you are not bothered about the energy of the particle or energy of the atom. There actually you can relax your degrees of freedom of the energy, and but you have to squeeze, okay, your position quadrature. Okay. So that is one of the example where actually you can use it. So energy you don't bother in the case of atom in the electron microscope. Okay. Now, so what about the energies of the squeezing? So if you just calculate the Hamiltonian with respect to the squeeze state, okay, what you will get? You will get half h cross r. So this is, remember we are talking about squeezed vacuum, okay. So in normal vacuum it will be half h cross omega. Additional term what you will get, sine hyperbolic r square. So as you saw that these actually shootings off with the increasing value of the r. So what you say that this is the properties of the squeezed vacuum, and you can also use generalized expression of the squeezed operator. Okay, depending upon the how the R is behaving, as we explained that if the beta, that whatever the incoming pump state has some kind of a phase. Okay, so the global phase, if you have I phi, if you can add that, okay, so that will give you the some R phi. Okay, it will be stated R phi. So there is R phi dependence on the squeezing operator, and in that case, what you will see that if you want to calculate the dispersion of the position and momentum, okay, with respect to the squeeze vacuum, okay, what you will have? You will have the terms which is like this one: the sine cos hyperbolic square r plus sine hyperbolic square plus the will be terms like this one. Okay. Similarly, the momentum. And here you see that there is an extra factor cos phi, and cos phi, if you put that phi equal to 0, is nothing but what you just saw earlier, that you could get that in terms which is in terms of h cross. Okay, these are the terms in terms of h cross. Okay, it will be minus 2r, and sorry, this will be plus. Okay, and this will be it will be plus 2r. Okay, the momentum will be plus 2r. So one will be squeezing and one will be amplifying depending upon the value of R. Okay, and whether if you put phi equal to pi, okay, so phi equal to pi, again what will happen, that it will be changing the sign. Cos phi will change the sign. So your minus will be plus, plus will be minus. So wherever it was minus earlier, it will be plus here. Okay, it was mistake is a plus here, and here it will be minus. Okay, so changing the value of phi, you could see that what you got from 0 to pi, okay, you got that squeeziness in the position sector goes to the squeeziness in the momentum sector. Okay, and squeeziness in the momentum sector goes to the squeeziness in the position sector at the expense of the canonically conjugate quadrature. Okay, dispersion. So that's actually property of the squeeziness. Okay, so you can have a generalized expression for that. Okay, and sorry. So in the next class, what we will discuss about the squeeze coherent state. Okay, but what I discussed today, so far that we have discussed that how the squeezed operator can be written in terms of the creation and annihilation operator. So we understood that using the knowledge of the second harmonic generation or nonlinear process inside the crystal, we could write that SR operator, which is nothing but the squeezing operator. And once we operate that squeezing operator, the vacuum state will get squeezed vacuum. And we have seen that what will be the properties of the squeezed vacuum. And also we have seen that how the position and momentum quadrature, okay, the squeezing and amplification, okay, is changing over time. Okay, that's a very important phenomena which we have to understand, that the squeezing is not a permanent one, which goes actually which evolves with the time, okay, from one quadrature to the another quadrature. And thank you for your attention. I'm just finishing the time. Okay, so maybe I'll try to answer some of the questions or doubts which you have. Thank you.
Thank you very much, Professor.
Thank you very much, Sanjay. We had a wonderful discussion on the squeezed states today.
Sorry, some of the
Vinay, thank you very
questions.
much. And Vinay will take care of the question answer session this morning. Vinay?
Yeah, thank you, sir. So there are a couple of
Vinay, your mic needs to be unmuted, I think. We are not able to hear you.
can you hear me now? Am I audible now? Yeah, now probably.
Yes, now we can
Yes.
hear you better. Yes.
Okay, thank you. Yeah, so there are a couple of questions on the chat box.
Right.
First one, I think you already answered. So let me go to the next one. This is by Girish. So the question is, how can we determine that photon is interacted with virtual state or real state?
Okay. Yes. So, you can determine easily. Okay. So what would happen that you can see that if you interact the photon with the real estate, okay, like you are interacting with the, I think talking about the interacting with the matter. Okay. So in the case of the matter, depending upon the frequency of the photon, okay, either it will be absorbed or it will be scattered. Okay, so if it is absorbed, what would happen that you will get the excitation in the matter. Okay, and subsequent de-excitation, okay, will show that okay, the photon has gone through that, and the absorption with the by the real state or the energy state of atom. If it is just scattered or if it just passed through, like something called as transparency, okay, through the matter, okay. I'm not going to EIT, okay, just so electromagnetic induced transparency, that is different thing. So when actually the light is not being absorbed because of the having different frequency of the compared to the transition line, okay, light will just pass through, and that time you just look at the emitting light, okay, and compare with the incoming light, and just see that whether it has interacted with the inside the matter, okay, it is some absorption or emission taken place. So by that way, you will be able to realize that interaction is happening, happening with the real state or not. Okay. Also, so if it is actually you are talking about the interaction of the virtual state, so in terms of the field theory, when you talk about, okay, when an atom is going through the this kind of emission and absorption process, in between there is a possibility that there will be a lot of internal absorption emission process going on. Okay, those will be able to understand in terms of the virtual state. Okay, so our virtual process. Okay, so one of the example, okay, of the virtual process is that when you want to see that that measure the charge of the suppose one electron. Okay, so if you see that the charge of the electron, okay, and if you compare that with a Baird charge, which you know already, okay, and if you compare that Baird charge with the measured charge, okay, which you see it is different. That's because, okay, that you will see that from the electron, okay, there will be some kind of a pair production happened because of the virtual photon around this, okay, around the electron. Okay, this pair production, okay, depending upon the which charge, whether it's a positive or negative charge, so it will actually attract opposite charge, and you will get a screen of the opposite charge around the Baird charge, and ultimately you measure it. And this is actually one of the finest actually proof of the quantum electrodynamics, which have been measured at the level of 10th decimal places. Okay, so experimental and theoretic actually they are matching up to 10 decimal places. Okay, and there actually you will be able to understand by comparing the Bayer charge and the measured charge, there is the existence of the virtual particle, okay, or virtual photon or virtual electron positron. Okay. So that's actually give you idea. So what actually you have to do, you have to understand that in terms of Bayer system and effective system. Okay. So when you see the effective system, there will be a lot of virtual process may going on. Okay, that you have to measure it and compare it with the Bayer system and understand. I believe that answers to your question.
Yeah. So the next question is by Asit Barik. So why are coherent states important?
Yeah, very good question. So it has actually explained in the last class also, the last one of the last classes. So what happened that as you saw so far, that coherent state, okay, can be behave like your down state or no photon state, like a vacuum. What is important that dispersion dispersion is minimum for the coherent state. Okay, that means that it's like a laser light, like when you have a laser pointer, you are able to point with the laser pointer. Okay, that's because that dispersion of the laser lights is very, very small. And you know that laser lights are the coherent light. Okay, so that when you have a coherent state, okay, you can have the minimum dispersion and work with that light in the experiment, and it will be useful. Okay, because if you have a dispersive light, you will not have a control on them. And as you understand that laser light is one of the very successful in day-to-day life, in many experiments, many kind of operations. Okay, so all those things are controlled by laser light. So that is because of its coherency. Okay, and also that you can change the intensity. That is a very important quantity. Change the intensity of the light, the number of photons inside the light, and still keeping the system as a coherent. That means non-dispersive. That is very important.
Okay, so he actually has one more question. So how do we make a squeezed vacuum?
Oh, yeah. So we'll discuss that in the next class. Okay, that process. So we actually use the local. So like you remember that how we have worked on the beam splitter. The beam splitter, as you know, that there's a two input ports are there. Okay, or orthogonal input ports. One of the orthogonal input port you will have a local oscillator. Another one will be vacuum. So you will see that I'll explain that in the next class. That the experimental procedure. Okay, how using the beam splitter and how with the help of the local oscillator you can get the vacuum squeeziness. So just please wait for the next class.
Okay, so the next question is from Tushti. So what is the physical meaning of the angle phi in the generalized squeezed operator?
Very good question. Okay, so physical meaning is that, so as I said that, okay, when you have that incoming pump light, okay, I just wrote it in terms of B. B is the annihilation operator corresponding to the incoming light, okay, the pump light, okay. Now, so that one I wrote in terms of the amplitude and phase, okay. When you talk about phase, okay, that's like electromagnetic field can have a phase, okay. That phase can come due to that propagation to the different media. Okay, like one of the example which I shown in the magenta kind of experiment, where actually one of the light passing one of the path, okay, through that some kind of a media where actually you have a different refractive index. So that refractive index will give extra phase to that. So this is apart from the propagation phase. Okay, propagation phase is that kx minus omega t. Apart from that, you can get extra phase. So if you can have the extra phase in the light, that also can be understood. And that extra phase can be utilized here. So that extra phase is you can gain in the light, okay, by having propagating to the medium or some other medium, okay, some other process, okay. So that's phi. Actually, that can be controlled, okay, as you can change the thickness of the extra medium which you are keeping on the way, okay, that you can change it. So phi also can be changed, okay. So that phi is the phi which we are talking about here. I believe you can visualize what I said, because if you can remember that how we could get the phase shift in the magenta kind of experiment, Okay, you can realize this.
Okay. So the next, it's slightly longer question. Bharat, do you want to ask directly if you're, or should I read out? Bharat? Okay, no response. So maybe I will read it.
Okay, fine.
Yeah. So in the slide where you introduced one photon, two photon processes and some frequency generation SHG, we can see from the figure that the excited state in the two photon process is a Rydberg state. In the case of SFG and SHG, the excited state is a virtual state. So my doubt is, what is the importance of virtual state here? Also, why can't we use Rydberg state, metastable state?
Okay, let me. So he is, I think, referring to this slide.
Yeah.
Okay.
So what is the importance of the virtual state? I think that is a central question.
So yeah, he had a similar question earlier. So
Yes.
yeah. So that, see here, what I'm saying that is that what you are saying, the virtual state, as I said that the here what we see that we are shining that two lights. Okay, in that, if you can see my cursor. Okay, along the red line, red arrow. So here we are shining two lights. It can be both of them are same frequency. It can have the both of them are different frequency. Okay, these two lights are incoming in the material or matter. Okay, and what we see, some two light, some one photon is coming out. Okay, which is coming out physically. Okay, so these are all physical things which are talking about. Now, in between, what is happening, that is actually we don't know. Okay, that is called nonlinear process, and that's why actually virtual states are coming in play, coming role to play. Okay, so what is happening that these two photons can combine and give you the excitation like this one. Okay, and what would happen then? These can go to the take the electron from ground state to any excited state corresponding to the energy which is pumped in that through the two photon. Okay, and then it can decay down to any subsequent down lower energy state. Okay, we don't know. Okay, and then from there we can have the spontaneous emission. Again, it will go. So that is the what is happening that in between there may be many virtual transitions possible. Okay. Also, so what we see it here, that we are just shining two photon incoming, which is physical, and we are getting one photon having the energy, just adding up that two incoming photon. Okay, so that is the physical thing which you saw. Inside there may be lot of process going on, a lot of transition is going on, which actually through the virtual photon or through the virtual transition, what you can say. Okay, and you can have that here. What we're saying, that spontaneous emission. You could have it as stimulated emission, as we have shown in the last picture. Okay, where actually you can shine one photon here, another photon having two omega. Okay, and ultimately you can get the one single photon having omega. So stimulated photon, you have advantage, as I said earlier also, that you can guide in the direction of the stimulated emission. Okay, unlike the spontaneous emission, the spontaneous emission can be any direction. Okay, it doesn't have any preference direction. Okay, it can emit in any direction, but a stimulated emission can be guided. Okay, and so you can have both the possibilities. The either two photon coming, giving you two omega one. So these are the physical quantities, and this actually you will be able to observe it. Or you can have one omega one and two omega one, giving you the emission of single omega. So these are the physical photons, okay, which we observe it. Okay, and in between the crystal, because of the deformation of the polarization. So once you shine the light, what happens? That your crystal is deformed. Okay, these charges inside that, the electrons, they will be deformed, and you will get the polarization. So you can get the polarization linear to the electric field, okay, or you can get the nonlinear to the electric field. Okay, so your process here, okay, chi2 is a nonlinear. Okay, so the nonlinear effect which actually goes there, and that can give you that that is a possibility that these two photons will be absorbed and giving you a single photon, which is physically can come out as a energy with the combination of these two photons. Okay, so those are physical processes, and virtual things, whatever you are saying that is inside the crystal, we will not be able to observe that. Okay, so that we have to explain theoretically that what are the physical processes going on. I believe that answers to a question.
Yeah. So Bharat, if you want to have any follow-up discussion, you may unmute yourself.
Yeah, you can just unmute and
Vinay, I'm not sure if Bharat can unmute himself. Maybe we have to ask someone else.
Okay. So he says in the chat box that answers my question.
Yeah.
I think there's no further clarification required. So these are all the questions we have. Any other question that the participants want to ask?
Looks like we are ready to conclude the session.
Yeah. So there are no further questions.
Yeah. Thank you, Vinay, and thank you, Sanjay, for bringing out these intricacies of the squeeze states. I think this was a very helpful session this morning.
yeah, I think next class when we do the experiment, it will be further understood. Okay.
Yes, yes, indeed. Sanjay, I'm sorry, tomorrow I will have to miss your class because
Okay,
there
no
is
problem.
some other meeting which I am not able to,
No problem.
reschedule. But somebody from the Center for Atomic Molecular Optical Sciences and Technologies will be
Okay.
here and they will conduct the proceedings. So thank you, Sanjay. And thanks to everybody. And thank you very much,
I'll
Vinay, for
stop
conducting
sharing.
the session. Okay, goodbye.
Thank you. Goodbye.
Yeah. Bye.
Goodbye.